Hello, everyone. Today we are going to start next chapter, chapter 7, which is going to cover techniques of integration. Basically, in this chapter we are going to learn how to integrate almost anything we probably need in future life. We are going to start with a little review of what we already know about integration, and then learn one more method, which is called integration by parts, which is going to be section 7.1. Okay, so we are going to, as I said, start with review. Give me a second. And let's kind of review integrals we already know. Let's start with the simplest one. And the integral is going to be power function, x to the power of n dx. So what we are going to have are indefinite integrals which are basically antiderivatives of these functions, right? So we know the rule for a power function is add 1 unit to n, divide by the power which you have resulting, and don't forget about constant. Restrictions. You cannot allow n to be equal -1. So n is not equal to -1. Why? Because we special integral for n equals -1. Remember that when n equals -1, we are going to have integral of 1 over x. And in chapter, I think, 6.4, we learned that this one is not going to be a power function, but rather is going to be logarithmic function. So I'm going to put it as number 2. So guys, integral of 1 over x dx, which is kind of the case when n equals -1, is going to be equal ln of absolute value of x plus constant, right? And we just learned it recently, right? Let's now do more integrals we learned recently. Remember exponential function integral, e to the power of x dx, very nice function. Integral of it equals the function itself, right? Plus a constant, very nice function, right? Maybe next to exponential function or exponential function with base e, we should consider exponential function with any base. So here the base is e and the integral is equal e to the power, right? Here this is any other number, not e. What is going to happen? How the answer is going to change? Remember that we are going to have the very same function similar to e, but divided by ln of a plus a constant. In case the base is equal to e, in denominator we are going to have ln of e, which is equal to 1, and the formula number 4, it's actually going to turn into formula number 3. But I want to set these two formulas separately because formula number 3 is going to appear a lot in our work and formula number 4 maybe never. Okay? So we are done with power functions and exponential functions. Let's move to trigonometry. And next integral you learned long time ago, and that's integral of cosine of x dx. Well, remember cosine is the derivative of sine, so we are going to get a sine of x plus constant. Number 6, integral of sine of x dx. Well, sine is actually derivative of cosine, but it has a minus in front. When you differentiate cosine, you get minus sine. So we are going to compensate for this minus and place it in front of cosine. Now, when you differentiate negative cosine, you are going to get positive sine. Trigonometry, right? Let me see. We also had a couple of integrals which we calculated as formulas, and maybe it makes sense to give them two. Number 7, well, secant square of x. You remember that secant square is a derivative of tangent. So we are going to add it to our table of integrals. So maybe guys, I'm going to kind of squeeze it a little bit and move to the second to make a second row. So this or here, and kind of put number 8 or here. So guys, what other integrals we know? Well, we learned some in inverse trigonometric functions, we learned some weird integrals which were looking like this. Integral dx over square root of 1 minus x squared, right? And we learned that this integral is arcsine of x, right? So actually, when you differentiate arcsine or sine inverse, you are going to get 1 over 1 minus x. So obviously, that's going to give us antiderivative. For arctangent, derivative is 1 over 1 plus x squared, right? Means that the integral of that function is going to be equal to arctangent. Yeah, guys, I use sometimes arc functions, not like inverses, but you understand that arc functions and inverse functions are the same. So what other integrals we learn? Oh, just 9. Well, actually we learned some hyperbolic functions integrals, right? And maybe it makes sense to go like or maybe at least one or two hyperbolic functions. Sorry, guys. Remember that I told you that we are not going to use them a lot, but sometimes in the book you are going to see them used. Remember that when the derivative of arcsine doesn't have minus but has plus, it's going to become sine hyperbolic inverse, right? Instead of just sine, it's going to become sine hyperbolic inverse. Something happening to my pen. One more, number 11. And when you do have dx over 1 minus x squared, similar to arctangent, right? It's going to give us hyperbolic tangent inverse. You can write down hyperbolic arctangent alpha. So they are kind of symmetrical. There is one more integral which we calculated in lecture or in class, which I want to write down over here because, well, because we did it once already, right? And that was, I think, one of the problems we covered in class. So integral of tangent of x dx. It's still dealing with trigonometry, but it was not directly antiderivative of anything. If you recall, that was equal to ln of secant of x. Sorry, maybe I should make it a little bit smaller, so I'm going to fit my constant. How this happens? Remember when we learned about ln, we actually were solving a problem of tangent, and tangent usually represented as sine over cosine. And then you do substitution of cosine, which is going to turn it to ln of 1 over cosine, minus ln of cosine. When we bring minus inside, it's going to become secant. It was one of the problems we had in class on Wednesday, solving like after that lecture. Well, if you don't believe me, you can just differentiate this expression. You are going to get tangent. And these are good integrals to keep them in a short memory. So we don't need to go to the table every time we need to use one of them. And this is just a review, right? We are going to learn something new right after. So now we are going to move to integration by parts. Guys, maybe I just grab this integration by parts and move it down here and kind of because we are going to work right now. That's a new material we are going to cover. We are going to do integration by parts. Oh, something went together with integration by parts, I think. Oh, yeah, the top of this x plus 1. How about I move it back. It's not supposed to be here. And some extra stuff. Okay, So integration by parts. Well, guys, before we do really integration by parts, let me remind you. Remember, we have a substitution rule, which we learned in Calculus 5a when you kind of use substitution in cases like this. For example, you have sine square of x multiplied by cosine of x dx. Maybe not cosine of x. So here, like to solve this problem, usually we are going to use substitution, right? You can solve u equals sine of x, then du is going to be cosine of x dx, right? So this is basically going to be your du, and this is u squared. So you have u squared, du, and eventually you integrate this, just a power function, u cubed over 3 plus a constant, or you go back to sine, it's going to be sine cube of x over 3 plus a constant. What I'm trying to say, when you use this substitution rule, actually the result is going to be a composition of two functions, a cubic function and a sine, right? Sine inside of the cube. Maybe I'll make it more explicit by erasing cube and kind of writing down. Come on. Something happened to my pen. You should never use eraser. Okay. Yeah. It works, but works overwhelmingly. Okay, let me erase it back. Sine of x cubed, actually, right? That's composition of two functions. And substitution rule, it's actually kind of inverse, or substitution rule is inversing the differentiation of composition. When you differentiate composition of two functions, you differentiate inner function and then you differentiate outer function, multiply them, right? So when you see something like this, you are going to guess that probably this rule was used, and we kind of go reverse it by making a substitution like inner function and then go back to outer function. So the substitution rule inverses differentiation as a composition, right? Integration by parts is going to inverse product rule. Let's kind of see how it works. So let's write down product rule. Product rule. You probably remember that when you differentiate f multiplied by g, product of two functions, d dx, you are going to have the derivative of, let's say, second function by x multiplied by the first, and then derivative of the first function multiplied by the second, right? That's a product rule. So how to reverse it? Well, we're going to integrate both parts, this side and this side. What are we going to have over here? Over here, guys, remember that integration and differentiation are kind of inverse operations, right? And we are going to just get f multiplied by g. What are we going to have over here? I did not put dx over here. It's supposed to be when you put integral sign, supposed to put dx over here, right? What are we going to have here? Well, you can split it into two integrals, f, and when you multiply dx here and dx here, you're going to have f by differential of the function g plus g multiplied by differential of function f. I cancel dx. This is not really like theoretically valid operation, but the idea is like if you go back to the integration as a summation, so this dx is actually delta x, and this dx is actually delta x, and you can kind of cancel them. So what are we going to have in this case, guys? Well, now how do we use the rule actually? We are going to move this expression to this side and write down that integral of f dg is going to be equal f multiplied by g minus g df. So that's a formula of integration by parts. Let me kind of circle it. And well, because I was writing down this like product rule, I have actually unknown integral, which is over here on the right side, but normally we have it on the left side. So actually this one is supposed to be equal to this and goes in this direction, right? But because I wrote it already like that. Okay, let's kind of just rewrite it later. So what is necessary to kind of understand here? Imagine that somebody gives you integral, which looks like half of use of the product rule. Then you can use the second half. And in some cases, you probably are going to look at this expression and say, well, we had one integral, now we have a function and still another integral. Yeah, but maybe you cannot find this integral, which is on the right side, but you can find the integral, which is on the left side. And usually, after you do a couple of examples, you start understanding why people are using this. Because sometimes they see the products or functions which are looking like a half of the product rule. And sometimes it's easier to actually integrate the second half of the product rule. Okay, let's use this product rule on something just to see how it works. So I'm going to start with a very kind of basic example. My example number one is going to be x multiplied by sine of x dx. No substitution is going to solve this problem. Why? Because you are mixing up here like power function and trigonometry. Usually substitution is not solving it because they are not like powers of each other or functions of like compositions of each other or whatever. So there is no other way to calculate this integral except to understand that you can get this function only as a result of differentiation by using a product rule. So I'm going to kind of make arrows to show what is going to be what in my integral. So guys, my f is going to be x. My dg is going to be expression sine of x dx. Well, if I write it down as a d of some function, which function will need to differentiate to get sine? Well, we'll need to differentiate a negative cosine of x, right? Remember from our table, you differentiate negative cosine, you get sine, right? So, according to my formula, my function f is x. What is my function g? If I compare it to the expression over here, whatever sits under the d sign is minus cosine. So my function g actually is minus cosine. And if I write down the left side of my expression, I need to multiply f by g, which is negative cosine of x, and then put minus, and then put integral, copy my function g, which is minus cosine of x, and then find df. Well, because my f is x, my f is x. My df is going to be what? Derivative of x, which is 1 by dx. Well, I'm going to just copy it, but you really don't need to copy 1. And if you continue simplifying this expression, you are going to see that we have minus x cosine of x, right? Here, two minuses are going to give you plus, and under the integral, you don't have a product of power function and trigonometry anymore. You just have a plain cosine. The integral, it's one of our table integrals, right? And we are going to have minus x cosine of x. Integral of cosine is just sine, right? And plus a constant. So this is going to be the example of use of integration by parts. What was my trick here? Well, I kind of noticed that if I differentiate sine, it's going to give me cosine. If I differentiate cosine, it's going to give me sine. But if I differentiate x, it's going to give me 1. So actually, it's going to disappear from the integral and kind of let me continue it without like a second function. And that's the trick I'm using. So sometimes it's more convenient to rewrite this expression in the term of other integral, where you see that differentiation of a second function is going to probably eliminate it or make it slightly kind of better or easier. Okay? my next example is going to be about exponential function, guys. So how about x? I'm going to do x squared multiplied by e to the power of x. So that's my next example. So here, guys, why we need to use by parts? Well, again, exponential function and power function totally coming from different pools. And you cannot do substitution here, or you cannot kind of bring them together as a substitution. How integration by parts is going to work? Well, you will need to kind of, for integration by parts, to use the formula. You'll need to find f and g, right? So here, guys, I'm going to set up my function f over here and my function g over here. How do I know that e is going to be function g? Well, actually, this one's supposed to make a dg, right? But which function supposed to be differentiated to give me e to the power of x dx? Conveniently, it's supposed to be just e to the power of x. If you differentiate it, you are going to get this expression. So in this case, everything is simple. Your function f is x squared and your function g is e to the power of x. And according to the formula, you first have to multiply them. So x squared e to the power of x, then minus, then integral, and then you copy the function which was differentiated, and that was exponential function, right? And you differentiate the function which was not differentiated under the integral. Not differentiated is x squared, so 2x dx. If you're going to look at this integral and oh, and we still cannot integrate it. It's a little bit better than the previous one, but it's still not good, right? And when you see that integral is improving in the way you are doing your integration by parts, that's a good sign, like with L'Hopital's rule, that you are on the right way. Why don't we use integration by parts second time? And again, you see that a function which is improving actually is x, like 2x, because before it was x squared, now it's 2x, and if you differentiate it one more time, it's just going to be 2, right? For exponential function, no matter how many times you differentiate it, it's not going to improve. It's still going to be e to the power of x. So it makes absolutely no sense to use it as a function differentiated under the second integral. So what I'm going to do, guys? Well, I already kind of considered that e to the power of x dx is going to make dg, and g is going to be e to the power of x. So I'm going to write down g equals e to the power of x. That's for second integral. What is going to be my function f? My function f is going to be 2x. So let's continue. I'm going to continue over here, okay? So I'm going to copy my first term, and then I'm going to put minus, which sits in front of the integral. And after that, I'm going to apply the rule. So I'll need to multiply f and g. So it's 2x e to the power of x, f multiplied by g. And I need to put minus integral, and I'll need to copy my function which was differentiated under the integral and was exponential function. And I'll need to differentiate the one which was not, 2x. Derivative of 2x is going to be 2. And we are almost done, right? Look at my integral now. It has no x at all. It has just exponential function, and basically it's a table integral. So you just need to finish integration. I'm going to put one more line over here, x squared e to the power of x minus 2x e to the power of x. And if I distribute this minus over this one, I'm going to get plus integral of e to the power of x is e to the power of x, and 2 is going to become a constant in front, and they're going to be a constant as an indefinite integral. You see? So I used integration by parts 2 times, and I kind of found my answer. What would happen if I kind of identify the functions which are f and g wrong way? Because looking at product of two functions, how do you know which one is f and which one is g? Let's do this. So this is going to be a bad solution or wrong solution, but you will need to see it once. So when you see it on your own in your like homework or whatever, you're going to guess, yeah, I'm just going to do it the wrong way and I'm going to cross it and move to the right one. So guys, what is going to happen if you identify your integral opposite way? If instead of identifying x squared as f, you are going to identify e as f, then x squared dx is going to be your dg g, right? If it's dg, which function you differentiated to get x squared? You have differentiated x cubed over 3, right? Because you differentiate x cubed, it's 3x squared, right? If you divide over 3, 3 is going to disappear, and that's going to be x. So your function g then is going to be x cubed over 3. And let's apply it to the formula. So copy f, then copy g, and then minus, and the integral, and then copy g because you already kind of, it was derivative under this integral, now it's becoming function under this. And then differentiate e. E to the power of x derivative is still e to the power of x. And now look at your result. Do you see that when you did this one step of integration by parts, your function under the integral has become more complicated, like it was x squared, now it's x cubed. At this point, you're probably supposed to guess, maybe my choice of functions f and g is wrong. And usually when you realize it, you just need to cross this and kind of rearrange them. And it's normal to do mistakes like this at the beginning. Because, well, you don't know really, you don't have any experience. After a while, after solving several examples, you are always going to guess correctly. Well, for example, I always guess correctly which function is supposed to be f and g just because I did many examples in my life. See? Okay. So now I'm going to consider example which is not typical, but also good to know, because this is already going to be a trick, not just a plain use uh, of the rule, but a little trick. Guys, what is going to happen when you see integral like this? There is no second function. And you basically don't know. How do I use product rule if there is only one function? Because there is no product. Well, guys, you always can add or like, let's say, multiply your function by 1 and represent it like this. And then do your like kind of assignment of f and g. Here, it's going to be kind of easy. Why? Because, or for example, if you want to assign once one is supposed to be f, one is g, and actually g comes like a derivative of something. You really, guys, don't know derivative of what is ln. So here, there is no, like, you don't have any options. If you want to call this dg, then you don't know what is integral of ln, because actually that's what we are trying to calculate. So this one cannot be dg. So your dg is going to be this one. This is dg, and this one is going to be your f. Well, which function you differentiate to get 1? You know that you differentiate x actually, right? Derivative of x is going to give you 1. So let's try to see what are we going to have if we spread it this way. So we copy f according to the formula, right? Multiplied by my function g and then put minus. And now we copy function g and we differentiate what sits under the integral, ln. And derivative of ln is just 1 over x. And look how nice is our integral looking after that. Guys, I'm going to put x in front of ln because if I put it after, it's going to look a little bit confusing, like, am I multiplying two x's first and then take ln, or like, if you put x in front, it's kind of obvious that you multiply x by ln. So if you cancel these two x's under the integral, we're just going to have integral of 1, right? And the integral of 1 is just x. You differentiate x, you get 1 plus a constant. And guys, this example number 3 is a good thing to remember because we actually now know what is integral of ln. Before we did not know what is integral of ln. We know integral of sine, cosine, inverse of sine, cosine, tangent, secant, square, and other stuff, but we don't know what is integral of ln, and that's what is integral of ln. In some books, you are going to see simplified version of this integral, which is going to look like this, ln of x minus 1. I don't know. Maybe if you just remember how to calculate. So guys, whenever you deal with sine and cosine, your g is sine and cosine. Whenever you deal with exponential function, your g is exponential function. But with logarithmic function, your g is actually the power function. A little bit strange, but that's how it works. Okay? Okay, guys, let's consider another example. It's going to be example 4. And here, guys, we are going to calculate a definite integral. Definite integral is area under the curve. We are going to see how integration by parts works if we integrate or use Newton-Gibbons formula or find area under the curve. This is another case of finding integral, which we actually don't know, right? We don't know what is integral of ln. We don't know what is integral of arctangent, which are like inverses. We already know what is integral of tangent, right? But for arctangent, we don't know. We're going to apply the same technique we used for ln. So we are going to care about our limits later. But for now, guys, because it's just one function, we can always multiply it by a factor of 1 to make it product of two functions. Now, guys, which one is supposed to be differentiated here in the second integral? Well, we understand that if you differentiate 1, it's going to give us 0, and probably there's going to be no second integral. So maybe we need to choose 1 as our dg function, right? So 1 dx means that function g equals 2x. Well, function f, whatever is left, it's tangent inverse, right? And kind of let's continue. Let's use the formula. You scroll it up. So I'm going to put equal sign. And, sorry, we'll need to multiply g and f first, right? X and tangent inverse of x, and then subtract. And, sorry, not equal sign, but subtraction sign. And subtract integral. So now we are going to copy function g and differentiate what is like, and I forgot x over here, and differentiate our function f, right? The function which was not differentiated under first integral. Remember that derivative of tangent inverse is 1 over 1 plus x squared. Now, guys, this integral is a little bit better because it moved us from like inverse trigonometric function to just like rational fraction, right? But still, we don't know how to calculate it, and we're going to think, okay, what should we do in this case? You cannot use integration by parts anymore, just because, well, if we differentiate anything here, it's just going to become worse. But what we can do, we can use substitution. And let's kind of look at the expression of the fraction. You see that fraction, besides a derivative of tangent inverse, also looks like a derivative of ln, right? Just the inner part of it is not like x, but 1 plus x squared. I'll try that. My substitution is going to be 1 plus x squared. What is going to be then my du? Well, if I differentiate 1 and 0, x squared is going to give me 2x dx. And it looks like I already have x dx here. So if I divide this by 2 and this by 2, I'm just going to have du over 2. So what I'm going to do, guys, I'm going to copy my first expression, so I'm not going to forget about it. Tangent inverse of x, and then minus, and under the integral, I'm going to put du over 2 instead of x dx, and in denominator, it's just going to be u, right? Because we labeled it as u. Well, now we can see clearly that our integral is going to give us ln, all right? And I'm going to kind of copy my first term, tangent inverse of x, and minus 1 over 2. I'm taking this 1 over 2 in front of the integral. And under the integral, I'm going to put, under the ln sign, I'm going to put absolute value of u. Now, because I have x and u, I'll need to go back to original variable everywhere. So I'm going to have x tangent inverse of x minus 1 over 2 ln, instead of u, I'm supposed to plug back 1 plus x squared and put absolute value. But if you look at this expression is not only greater than 0 because x squared is always greater than 0, it's actually greater than 1. So I'm not going to put absolute value because I already know that this expression is 100% going to be positive. Well, usually I put a constant here, but if I go back to original problem, I see that I have limits over here. So I don't need to put a constant here, but I'll need to plug in my limits. Upper and lower limit and use Newton-Leibniz formula on this integral, right? So I'm going to plug in 1 first, and that's going to be 1 tangent inverse of 1 minus 1 over 2 ln 1 plus 1, right? And then minus, and I'll need to plug in 0. 0 here is going to turn everything into 0. And tangent, by the way, inverse is also 0, right? So what I'm going to have over here, minus 1 over 2 ln of 1 when I plug in 0 here. Who remembers ln of 1 is equal to what? It equals to 0, right? Remember the graph of ln which goes at x equals 1 exactly through 0. So this is 0. And my final answer is going to be, let me bring it up, tangent inverse of 1. What is tangent inverse of 1? What angle, tangent of which angle is going to be equal to 1? Well, we probably remember that's pi over 4, right? Pi over 4 is going to, tangent of pi over 4 is equal to 1, right? Multiplied by 1, which is going to still give us the same answer, and minus 1 over 2, and the ln of 1 plus 1, nothing special, just the ln of 2. And that's going to be our answer. Pi over 4 minus 1 over 2, the ln of 2. So, guys, most integration by parts are going to be used to solve specific problems. And actually, all my examples are touching these specific problems. It's not like integration by parts can be used to any integral. No, actually, there are some specific problems, and I'm going to cover all of them during the lecture. So we know how to integrate mixes of power function and exponential, power function and trigonometry, inverse functions of exponential as a logarithm, inverse of trigonometry as tangent. Now, guys, we are going to mix up together power function, exponential function, and trigonometric function. And we are going to learn interesting technique of calculating integrals using by parts integration. Example number 5. Yeah, guys, if you feel that many examples is too hard to have in one kind of lecture or whatever, you can stop at any time and kind of return to it whenever you kind of ready rest it a little bit, because this first section is long. So my next example is going to be a mix of exponential function and trigonometric function, mixing up exponential and sine. So usually, guys, our goal is to make sure that the second integral, by differentiating one of these two functions, is going to make everything improve. The bad thing for this integral is that neither of these two functions is going to be improved while you differentiate them. For example, you differentiate exponential function, it's not even going to change. You differentiate sine function, it's going to become cosine, but cosine is not much better than sine, right? And you are still going to get exponential and trigonometry. Yes, guys. And that's going to be resolved by doing integration by parts 2 times and then solving an equation. So what I'm going to do, guys, I'm going to combine exponential function and dx and call it my dg, from where g is going to be e to the power of x. It's very convenient because you differentiate e to the power of x, you're going to get e to the power of x. And my sine is going to be my f. Let's see what we are going to have. So first we multiply f and g, right? So I'm going to do e to the power of x and the sine of x. Now minus integral. And I'll need to copy exponential function. And I'll need to differentiate sine, which is going to give me cosine. And you probably are going to tell me, yeah, that's the second integral is exactly bad as the first one. Exactly, guys. And that's why I'm going to apply this second time. So again, I'm going to combine exponential and dx and have them dg, from where g is going to be e to the power of x, and my cosine is going to be my f. And let's see what we are going to have. Unfortunately, I'll need to copy everything or I can deal with integrals. So here, product of f and g is going to be e to the power of x cosine of x, right? And then I'll need to subtract the integral, and under the integral, I'll need to differentiate actually the cosine. Derivative cosine is negative sine, right? Wow, you are going to look at this integral and going to see, wow, that's exactly what we said in the beginning. Exactly, guys. And that's what we are going to use actually. We are going to make a loop, these two integrals. I'm going to write it down as one line and then kind of relabel fact terms in this expression. Cosine of x. And here, guys, if we have two minuses, we are going to have one plus. Oh, no. We have three minuses, actually. Minus, minus, and one minus. I'm sorry, we're supposed to have minus, actually. Somehow, whenever I use eraser, something happens to my pen. Okay, e to the power of x, sine of x, dx. And because we already did write this integral like two times, that's line number 3, I'm going to copy original integral in the beginning of this expression to kind of make my next step more transparent. Guys, what we see? We see integral e to the power of x sine of x dx on the left side and on the right side. What you can do, we can combine this left and right side of integral together. That's what I'm going to do. I'm going to take the whole thing and move it over here. Remember, I told you that we are going to solve a equation. Well, if I have one of these integrals and then I add one more because it has minus on the right side, but don't have plus on the left side, I'm going to have two of them, right? So I'm going to have 2 e to the power of x sine of x dx. What I have on this side? Well, I have e to the power of x, which I can take outside of parentheses, sine of x plus cosine of x, right? Now, guys, my goal is calculating the integral. It's not like to get the final answer by just eliminating the final integral and using the table formula. And if I divide this expression by 2, I'm going to have, I divide by 2 here and by 2 here, I'm going to have on one side the integral, which I'm actually searching to find, right? And on the other side, the expression is a function. So that's going to be my answer, actually. So that's it. That's how we calculate the integral. That's a special technique. It's just kind of making a loop, turning your original integral back to it and combining it together. It's not going to work for everything, but it's going to work for a mixture of exponential functions and trigonometric functions. What else? Well, guys, we're going to do one more integral, and that's going to be called a reduction formula. And I think because it's kind of long, so you can kind of stop for a second and continue watching it. So reduction formula, my last example, example number 6, reduction. Reduction formula means that we're not going to actually calculate any integrals at the end, but we are going to give the formula which will going to help us to solve some integrals. Please watch how I do this reduction formula. I'm actually going to use a similar technique to what I used for exponential and trigonometric function mix, but it's going to be longer, not more complicated, but a little longer. So I'm going to integrate sine to the power of m of x dx. N is just a real natural number, like 1, 2, 3, 4. Well, for 1, we probably don't need it. We do have the integral. But 2, 3, 4, and any others, we need them. Well, guys, here we don't have a product of two functions, but we have so many signs combined over here that we can always separate 1 or 2, right? And what I'm going to do, guys, I'm going to separate one sign over here. I'm going to have sine n minus 1, going to be a little bit general, and the sine of x dx. So I took one of these n signs and separated it to eventually use integration by parts formula. Now, guys, I'm going to call this dg, from where g is going to be which function we integrate to differentiate to get sine, minus cosine, right? And I'm going to use integration by parts. So I'm going to have sine n minus 1 by negative cosine minus integral negative cosine my function g, and I'll need the derivative of my function f, right? This was my f. So what I'm going to do, I'll differentiate it, but because it's a composition of the power function at sine, I'll differentiate power function first. N minus 1 sine to the power of n minus 2 of x, right? The power is going to decrease by 1 unit. And then I'll need to differentiate sine. Derivative of sine is cosine of x. Yeah, it looks like integral is even worse, but let's see how it will go. So I'll need to copy the first expression. I'm going to put minus in front, okay, and put the cosine of 2 sine n minus 1 to the sine of the power n minus 1 of x. And here, I think I combine these two minuses to plus. And I'm going to put n minus 1, which is actually constant, can be taken outside of the integral, sine to the power of n minus 2 of x. And these two cosines are going to be combined into cosine squared. What I'm going to do with this cosine squared is I'm going to represent it as 1 minus sine squared. Remember Pythagorean identity that sine squared plus cosine squared equals to 1. And you can solve it for cosine and get 1 minus sine. You'll probably ask me how it works. Well, let's see. Minus cosine of x sine n minus 1, sorry, copying, plus n minus 1. I'm taking the constant outside of the integral. And under the integral, I have sine n minus 2 multiplied by 1 minus sine squared of x dx. Yes, I don't want to copy the first term. I'm just going to work with this integral, and then eventually I'm going to copy everything together. So if I multiply or kind of open my parentheses and multiply each of these two terms in parentheses by sine of n minus 2, I'm going to get the integral sine n minus 2 of x dx, right? And the second integral is going to be sine n to the power of n dx. Why? Because it's minus 2, but then we'll need plus 2 because there are two more signs here, right? And I'm going to now put everything back and minus 1 here, and I'm going to put this minus cosine of x sine n minus 1 of x here at plus, and I'm going to put original integral. Original integral was sine to the power of n of x dx, right? You probably already see why I'm doing this. You see that, sorry, it's supposed to be parentheses here because this factor n minus 1 is kind of belonging to both of these terms. You see that we do have sine to the power of n integral on both sides of this expression. Just over here, it's multiplied by n minus 1. So we can actually combine these two signs together because they're same integral, right? And that's what we're going to do. So I have one sign here, and then I'm going to add n minus 1 signs here. So how many of them am I going to have? Well, I'm going to have n of them, right? So I have one here, that's one here, and because when I move it to the right side, it's the left side, it's going to give me plus n minus 1. So n minus 1 plus 1 is going to give me just n, and that's going to be integral to the power of nx dx. On this side, I'm just going to copy everything. Minus cosine of x sine n minus 1 x and plus, sorry, plus n minus 1 integral of sine of n minus 2x dx. The last step I'll need to do, I'll need to eliminate this because I'm searching for just integral without any like multiples. So I'm going to divide everything by n. 1 and 1 are going to cancel, and I'm going to divide everything by n. So my integral is going to be equal 1 over n with minus, I'm dividing everything by n, all my terms, n minus 1x plus n minus 1 over n sine n minus 2x dx. And that's going to be my final answer, guys. Probably will ask me why my final answer still has an integral. Well, because I never told you that I'm going to calculate the integral. I said that I'm going to develop reduction formula. Reduction formula is actually allowing me to reduce the power of sine under the integral by 2 units. So my next integral I'll need to calculate has a sine in a lower power by 2 units. What I can do is that I can use this reduction formula again and reduce it by 2 more units and by 2 more units, and eventually either my final power is equal to 1 or it equals to 0 when it's like, 2 minus 2 or 3 minus 2, which is like when the final power is equal to 1, it's going to give me just integral of sine, which I know that's going to be minus cosine, right? If it's 0, that's going to be 1 dx, and that's going to just give me x. That's it. So usually we call it a formula because we will need to apply it several times depending on the power of n. If your power of n is equal to 2, for example, here, everything is going to be very simple. You're going to have 2 minus 2, which is going to give me 0, and this integral is going to be just equal to x. But if the power is 3, for example, it's going to be slightly different. 4, you will need to apply it 2 times. Do you need to memorize this formula? No, guys, you don't need to memorize this formula. Formula is kind of, there are too many minuses and minus 1 divided by n. And as I myself don't remember the formula, so I cannot require you to remember it, but you will need to remember how we obtain the formula, which is more kind of valuable. So let's go briefly over the steps, how we obtain the formula. First, we represented our sine to the power of n as a product of 2, n minus 1 and sine of n, sine of x, right? Second, we integrated by parts. Third, we used Pythagorean identity. Then we opened parentheses, and then we moved the integral back together, and we got a final answer. So usually, guys, for quizzes or tests or whatever, you're going to have a specific power of n there, like 7, for example, or 15, and then you will need to use it several times. So you don't need to memorize the formula, but you'll need to understand how to obtain the formula. Okay. Well, I think we can finish this section 7.1 at this point, and I'm just going to write down some problems for practice. Okay, guys, I wrote the problems to save your time listening to me. So, first problem, the product of x cubed cosine, so mix of trigonometry and power function. Second problem, exponential and x to the power of 7, the power function. Third problem, exponential and cosine, trigonometry and exponential. Fourth problem, inverse and the power function. And fifth problem, reduction formula. Here, I don't want you to use the formula. I want you to obtain the formula for specific power of 5 and reduce it by 2 units. Means that your final answer is going to have integral cosine cube of x dx. So you don't need to kind of finalize the integral. You just need to calculate, make one step of reduction formula. Okay? And I think that's it for today, and see you in class.